Hello, welcome to Designs for the Edge with Microchip Technology. Designs for the Edge is our live stream series in which we talk about market trends and system design challenges. We're in our second season of this live stream. We'll be broadcasting each week at this time through October 16th. Please like and subscribe and share the episodes, and also feel free to ask questions. We'll take questions from the audience at the end of our session today. I'm your host, Eric Glatfelter. Our topic today is adaptive lighting for automobiles, and joining me remotely is Stefan Kuba. Stefan, welcome to the program.
Hi, Eric. Thanks for the introduction. Yes, my name is Stefan Kuba. I'm Automotive Marketing Manager within our Automotive Products Group, and today I'm excited about the conversation and to be able to talk a little bit more about our adaptive lighting solutions we have in automotive.
Great, thanks Stefan. We're excited to have you here. So as a little bit of background, before we get into the state of the art today, let's just talk about lighting, the progression of lighting. So we've come a long way from where automotive lighting was, the state of the art was an incandescent bulb that could be on or off, right? Very simple. So would you just describe for our audience today some of the different parameters at play in the automotive lighting market today?
Absolutely. Yeah, as you just pointed out, it has been a long way from an incandescent bulb to new design features, to new technology-driven applications in exterior but also interior lighting, making them adaptive. And at the end, it integrated a lot of visibility enhancements from illumination effects, but also to close the gap to more style and safety features. At the end, a light on the vehicle is not only an illumination or visibility feature anymore. It is actually also a styling element. It defines the car's character, and it also adds more and more smart features. Intelligence is coming in, automated features. The car is getting autonomous. With this, also new ideas, new implementations, new applications are needed. Yeah, this actually goes a very long way from the past we have seen being just a bulb, which is on-off controlled, or which was on-off controlled.
Yep. Okay, so one follow-up to that, compared to incandescent bulbs, how do the LEDs and LED matrices compare as far as the amount of illumination provided and the amount of energy consumed?
Well, the major driver, as you just mentioned, is efficiency, to increase the level of illumination, to increase the visibility, raises in functional safety levels, but on the same time also increases in efficiency, reduces the power consumption. You can imagine in the past you had a couple of bulbs. Now you have started the evolution from a couple of bulbs to a couple of LEDs, maybe some strings or stripes of LEDs. Yeah. And then it got connected to very big matrices to increase the feature set, but also to increase visibility and illumination levels. And they had to be controlled with a more sophisticated, more intelligent way to reduce the energy level, the power consumption. And this gets even more important because of the car is getting from a combustion engine to an electric vehicle. And here, the extension of the range, the efficiency is a key design element.
Sure. So the capabilities are increased, but also the complexity of design with the integration that you talked about. So can you talk to us about the new lighting standards and the ecosystem?
Yes, there have been a lot of new lighting standards and ecosystems. This is key because you can imagine that in the past, when you just had an on-off control of the bulb, when the first LED design started, they also tried to copy and paste the design feature and also still did an on-off control of the LED. Let's just say on the previous slide once more. So you had actually a lot of new lighting standards evolved because of the dynamic feature set which was needed to drive the LED matrix. You can imagine you had an LED matrix which had to detect oncoming traffic, to turn off parts of the light source, to partially keep the street illuminated, but to turn off only parts of the high beam that are disrupting, for instance, from oncoming traffic or from cross-traffic drivers or even pedestrians to walk on the roadside. So with this, a lot of beam profiles and glare features got added, which needed to improve the functionality. And on the other side, you also got the possibility to add a lot of fading effects, welcome features, design elements into the LED lights. So this progression has happened not only on the exterior, where basically more fixed function color tones have been or are used in automotive lighting, like the white color LED, the red or the yellow color LED for the brake light or for the turn indicator, but also in the interiors, which came from grille illumination to the interior to make more RGB colored functionalities in the interior of a vehicle, and also add dynamic light effects to make welcome features also available on that side. And then with the fact that the car moved from a manual-driven vehicle to an autonomous-driven vehicle more and more, you have driver assistance features which let the car taking over the driving for some time, and maybe with an alert in advance, like 10 seconds ahead, it warns you that you have to take over the steering wheel again, the manual driving. And with this, you can imagine you have a lot of design possibilities in automotive lighting, also with regards to functional safety. Imagine you have a green interior color, but suddenly something happens, you have to take over the driving mode, and then it can warn you with yellow alerts or with blinking red that you have to take over pretty suddenly.
Okay, interesting. So yeah, go ahead.
Yeah, no, if you just go to your question about the different standards, of course there are a lot of challenges we have to accommodate to fulfill these requirements we just described, these different applications. And the key of this is the data rate. You can imagine in the past you just turned on and off the LED, but now you have to connect it with the camera system. You have to analyze this system, this incoming picture pretty quick in real time at the end of the day. And then you have to define how you want to drive an automotive matrix LED. Let's assume 10,000 of LEDs are driven like a pixelated display. And some parts you want to turn off the matrix LED function to have this anti-glare or anti-blinding features turned on, so that you don't blind the pedestrians on the street or the cross or incoming traffic. And with this data rate and synchronization, you need a lot of real-time performance, which needs an adaptation of the car architecture. On the communication side, of course, how this data is shuffled in the vehicle. So we'll talk a little bit about that. And of course, it also drives a lot of different standards on the LED side, and this is what we can show in the next slide.
Okay. So let's. So I think here we're going to walk us through some of the use cases, right?
Yes.
Okay.
Let's just show this kind of LEDs, and these kind of LEDs you see. No, previous slide, please.
Back. Sorry.
Yeah. So here you see actually a couple of brands listed. For instance, Isolet is an interior LED standard, which was basically pushed from certain OEMs, like BMW is using them for RGB interior lighting to make LEDs dynamic. There are other standards like from Osram, they do RGB LEDs as well, but also white LEDs with this kind of standard for either exterior or interior applications. With these kind of LEDs, you can do a couple of hundreds, a couple of thousands of LEDs. You can connect them together, and you can increase the data rate and the speed. While the third bullet point is just an example, which is a micro LED LED, which is actually an array of thousands of LEDs, 10,000, 20,000 of LEDs as an example. They come from Lumileds, from Nichia, from Osram, and they enable a similar kind of functionality for exterior lighting. What is the difference? At the end, the difference is the different use cases. Either they are for interior used or for exterior lighting used. You might need to take different kind of LED technologies. But what do they have as a common consensus together? They put intelligence into the LED. You can imagine with LED technology, which is LED is also a semiconductor product. There are also production batch differences, small nuances in the development of the LED, different color tones. So you maybe have one production lot, all of them have a red LED, but some of them have a slightly different color tone of the red. And the problem to solve is, of course, the manufacturing, that you ensure in the production of the car that you have a lot of LEDs used in interior and exterior, and you want to ensure always the same brightness level and the same color tone of the LED. And the second thing is, besides making these LEDs smart, to take over some kind of this calibration functionalities to ensure the same brightness, the same color at the same temperature, but also over the time. They also are defined and designed to drive for higher data rates. Yeah.
Okay. So how does that lend to implementation in the different use cases in the automobile?
Very good question. We have tried to put the different use cases on one slide. If we just look into the discussion before, where we said challenge is the data rate, the other problem is, of course, the synchronization and to keep everything in sync, of course, because with these kind of features, you want to add a lot of different applications in the interior, but also of the exterior. And now you can think and imagine of a really homogeneous light effect of the vehicle from the exterior to the interior. Like you can have, of course, a ground or floor illumination of the exterior of your vehicle. You can have a grille illumination, which goes hand in hand with some kind of welcome lights, which also goes to the rear lamp, for instance, on the front lamp as well. And the second thing is that, of course, the car itself in the past was not really suitable from the architecture to shuffle all this data in real time from the front at the rear, interior and exterior. So what's definitely helping is also the trend of the automotive, which is evolving from the domain-based architecture, which had a lot of different domains in the car, with a lot of different domain ECUs, and now it's going to a centralized ECU. As I mentioned before, you have, for instance, the example of the exterior lighting, where a camera is analyzing the traffic on a street, and depending on this analyzing, the light is on the matrix, displayed in full power, is shaded partially to have anti-glare features enabled or disabled, to maybe warn pedestrians which are walking on the roadside, to warn them specifically, all with one big LED module. And now all the data can come together to a big centralized compute unit, which is the central ECU in this case, which can do that basically all of this in real time. But it can only do this in real time if you have enough bandwidth to shuffle the data from the camera to the central compute and back to the LED. And this is why we see more and more Ethernet or PCI Express and high data rate standards coming into the vehicle. In this example, we have the centralized ECU connected to Ethernet. It could be 1 gig, 100, 1 gig Ethernet, 100 megabit Ethernet connectivity. And then it goes into the zones. And here in this use case, you see the side zones, the door zones, you see the rear zone, you see the front zone, and also interior as one zone to just make it as simple as possible. And then, of course, you have different LED standards and LED brands which are designed for the different use cases. Like on the rear side, you have brake light, you have red color LEDs, for instance. In the past, you just had a couple of LEDs on the left and on the right side. And now they are getting, it's getting more sophisticated. You have big design elements from the very left to the very right, a lighting sword more or less, which has a lot of LEDs in a string. And all of this needs to be driven very fast. And there, for instance, is a company which is doing drivers suited for these kind of applications, which is a company called Microchip. And here we have solutions to drive with our microcontrollers, these kind of drivers and LEDs. Furthermore, and on the front side, for instance, to come from the rear to the front side, you have front projectors or anti-glare features, these high matrix LEDs I mentioned, and they are, when we come from the more simple rear side to bigger pixelated matrices, like on the rear you maybe need 1,000 LEDs, on the front we talk about 10,000, maybe 20,000, sometimes even more LED matrices. And one example we have tried to show you in one of the videos. So this is one of a projector. You see here an LED projector. In this case, it's a 20,000 pixel matrix, which drives very high brightness LED on the front. You see here as an example a display where we just stream and play back some content. And we stream the data live onto the front side. There are different animations used to show you how this can be, how this looks like, how fast, how responsive the system is, how quick. And what you also see here, if you just look into the onto the front side, well, this is the second, this one here. You see the cable connected. You just see an unshielded twisted pair cable. So that's basically a 10-base T1S Ethernet connection, which streams this data, and it's fast enough, but also low cost enough to enable such kind of functionalities.
Okay.
So if we just come back to the use case slide once more, you see that beside the front side, we also have the interior. And I'm just wanted to talk a little bit about the interior because we have a nice demo which shows you what you can achieve with that. And this demo at the end is using interior LEDs for RGB, different color mixes. But of course, you can also imagine how this can be used for a grill illumination as well. So if we just look into the second video now, David. Here you see the utmost performance which we are able to do. So there are different kind of boards used which are stacked together. All of them have a 10-base T1S connectivity. And what you can see is that all these boards are totally in sync to each other. They're really in real time. We play back the video content, and on the same time you see this video content onto these LEDs. And of course, now you can imagine you can use this for an interior lighting feature, but you can also use this, of course, for very nice effects on the exterior of the vehicle, like a motor room illumination or a grill illumination. And also this is actually done with 10BASE-T1S Ethernet, because here we have enough data rate, and with 10BASE-T1S, the automotive involvement, it also offers real-time performance.
Right. So the real-time performance, does that get to the latency? You were talking about, the lighting is not only providing illumination, but in cases of anti-glare or shading or things, it's actually responding to the environment around it. So those are safety critical, right? They need very low latency. Does Ethernet provide that support for that system requirement?
Yes, with 10BASE-T1S Ethernet, we are achieving this zero latency and real-time performance. And in these demonstrator videos, which we are also showing at events as well, so you can really see them in real time, there is also a nice demonstrator which has a camera connected, and you can just swipe your hand or a pencil over the camera, and you see it really in exactly the same in the same milliseconds, the responsiveness.
Okay. So a little faster than the old CAN devices, where you just got to flick a switch and wait a while.
It's a very good point, because in the past, of course, and it still is the case that you have a CAN connectivity or a LIN connectivity for low-level lighting applications. But of course, the higher the data rate, the more responsive the system must react. The more we have to move away from, for instance, CAN-based applications, which is maybe suitable for 200, 240 LEDs to control them in real time. Versus if we talk about Ethernet, of course, we talk about 10,000, 20,000, or even more possibility of driving such kind of a matrix LED. Absolutely.
So that supports the latency and the increased bandwidth.
Exactly.
Okay. Okay. So I think we wanted to talk a little bit more about one of the demo setups.
Yes. So we talked about these different standards for interior and exterior. If we just stay on the exterior side, I talked about the micro-LED technology, which is basically the intelligent LED, which has tens of thousands of LEDs connected together. We also have OSRAM, OSP technology, which can be used for interior but also exterior, for instance, grill illumination examples. And I also mentioned, for instance, on the rear side, the possibility of having the LED matrix connected to a Microblocks driver, which is from the company Microblocks, which is doing drivers with transistor integration to drive on a very low-cost manner RGB LEDs or red LEDs, for instance, for the rear side module. And on this kind of applications, you would probably more go towards this solution, because this is suited for low cost if you have maybe a couple of hundreds to a couple of thousands of LEDs connected. Versus on the front side, when you talk about 10,000s of LEDs, you would probably more go into the micro-LED solutions. So if we go back to the Microblocks solution, and this is where we have one of our newest demos available. This is actually can be used for the rear lamp, but could be also used for side matrix LEDs. So here you see, for instance, on the door side, on the bottom, you see one of the displays which could be on the side of the vehicle, which gives the environmental people around the vehicle some indications what the car will do suddenly. And this is important because the car is getting more and more autonomous. So sometimes you have maybe a robotaxi, and it will probably tell the pedestrians around that they have to take care, attention, or they can go ahead. They can maybe project a pedestrian way on the floor, and these type of things. And if we go back to the demo picture, you see actually that we have on the right a couple of our demo boards used. So these are our standard development tools, for instance, which has one of our DSP microcontrollers used to talk to this macroblocks driver and to drive a couple of hundreds, a couple of thousands LEDs, either with one single platform or with a stacked platform. And you also see, for instance, the host PC, which has a connection, which is the LAN 8670, which is basically a nice tool. You see the PC display on the background of the demo. So you want to stream maybe videos on a PC, how you bring them to the development tools. There is the USB to 10BASE-T1S dongle. This is this LAN 8670 device, which can be connected to a PC or to a Raspberry Pi or to an iPad. And then via USB, you stream out the data directly to 10BASE-T1S. And in our case, you see the microcontroller used to drive these macroblocks drivers and furthermore, these pixelated displays. And in this case, you can say we as Microchip, we have different kind of solutions, 8-bit, 16-bit, and 32-bit controllers. And of course, you could have also used an FPGA or a very performant Cortex M4 based product to drive this macroblocks driver. But in this case, the beauty of this solution is that we designed this for absolute low cost, which is also one of the design challenges, obviously.
Sure.
And in this case, the DSP has core-independent peripherals, so we can use these core-independent peripherals to drive these macroblocks drivers without any CPU intervention. Basically, the CPU, because of the beauty of the implementation of these peripherals, its autonomous and autarkic capabilities, can drive these macroblocks drivers without CPU intervention, without MIPS performance, and therefore you can use the microcontroller for some other supervisory tasks, and you can take the lowest cost device in this setup as one of the examples.
Okay, so just to clarify, those boards these are standard development boards that customers can get access to as well?
Absolutely. So the USB to 10BASE-T1S dongle is accessible. The green boards which are stacked are, for instance, the 10BASE-T1S MAC-PHY boards, which are then as well standard boards which connect to SPI to our, for instance, Curiosity boards from Microchip, which you can buy, of course, on microchip.com.
Yep.
And absolutely, so we use standard boards, and we also showcase this then at trade shows.
Okay, great. And then final question about this system. We talked about some of the connectivity devices and the digital signal controllers. What other types of components does Microchip supply that are used on these development boards in particular?
Well, on these boards, you have a lot of connectivity possibilities. You have extension possibilities. So see where we connect the 10BASE-T1S stack. There would be also other possibilities, for instance, to connect a LIN transceiver, a CAN transceiver, or any other things on it. On the board itself, we always try, of course, to make use of our TSS total system solutions, and in that side, it would be, for instance, the power supply, the
Sure.
LDOs, the DC-DC converters, which we're implementing, and another possibility at the end of the day in such kind of applications, what we see is that you also buffer the images. Maybe you localize. One example is you have the central compute, which streams the data live. This is one of the examples. Another use case would be if you don't have enough bandwidth, you can also have maybe a flash, an SQI flash, which we also have for automotive, and store the image data or the animation data onto this flash. Okay. But at the end of the day, the beauty of these solutions is that the increased data rate, the bandwidth with Ethernet supports real streaming applications, and therefore you can remove the need, for instance, a buffering memory, which is at the end one of the design benefits.
Okay, so what's the future look like here for these systems?
Well, I talked about a lot of different standards, a lot of different LEDs, and this really depends on what preference the OEM, for instance, has. Sometimes they want to have dedicated technologies for their interior LED lighting or a different brand, and this defines what you're selecting, what you're choosing, whether this is Melipu technology, which is one of the interior lighting standards, or Osram's OSP, or iSLED and ILAS, or micro-LED. So there are macro blocks, a lot of different standards. And of course, the beauty of a microcontroller-based solution, if we take 10-base T1S as an external MAC and PHY connected to our microcontrollers, whether these are 8, 16, or 32-bit microcontrollers, the beauty on this one is, of course, that you can integrate it with other functions, other functionalities, like you want to add a touch functionality in it. You have this flexibility with an MCU-based solution. If you want to have a sensor and actuator, a motor driver, stepper motor for adjusting the level of the light, for instance. These kind of features you can integrate. But you can also see the challenge, probably with all these kind of different standards, interior, exterior, different OEMs want different feature sets and implementations. You can imagine that if you want to make one platform, you're really struggling in making one development platform out of it. And if we go to the next slide, please, you see that we have a block diagram that you have the microcontroller and the PHY externally, and you program your software development based upon the LED matrix you're choosing. And we at Microchip support you with supporting all these kind of standards we are describing. But if you want to look into replacing the MCU development with one single development with make the development simpler and also support it as a platform for all these various kind of solutions, we are creating a new device which we call an endpoint. In this case, it's the lighting endpoint. And the lighting endpoint is at the end set up to support all these kind of functionalities. The demos you have seen are at the end these lighting endpoint for supporting micro-LED technology, for instance, from Nichia, from Osram, from Lumileds. And this takes over the development. You don't have to worry about that anymore. You have your central control unit, you have the Ethernet connectivity, and this endpoint takes the data from 10-base T1S Ethernet and moves it over to the LED matrix. And the second big benefit of this is that this is not a microcontroller development anymore in this case, because an OEM usually wants to have different implementations in the design done. When doing a microcontroller-based development, they want a bootloader function, they want field over-the-air update, so you want to have one image which drives the application, but you want to bootload it on the same time and then you swap. So you have to you make redundant designs, double flash, which raises in cost. Sometimes they want AutoSAR, which is a software stack in the automotive industry, on top of that, which drives another flash size. So a lot of big challenges, which is solved when we have the lighting endpoint, because it's basically a fixed function device. No software updates are needed, no over-the-air updates. You can, of course, reduce cost because it's optimized for the use case and ready-to-use solution.
Stefan, wow, there is a ton going on, and it looks like it's not slowing down. It's accelerating what's going on in adaptive lighting here. So thank you so much for sharing your expertise. Truly daunting challenges and some really powerful solutions that are available. Let's pause at this time. I will look to my trusty iPad to see if we have questions coming in from our audience today. So the first question, so I think this maybe came in earlier, we may have touched on this. This is asking about the comparison between the CAN protocol and the Ethernet protocol. I know we talked about this a bit, but maybe you could comment a little bit on that with respect. Also, you mentioned PCIe. So, kind of how do we partition amongst these various protocols in the automobile? I know that's becoming very complex also.
Yeah, absolutely. So there are a lot of different standards now, maybe also here with different use cases. But if we just look into the central compute architecture, we have the sensor fusion, the camera integration with the LED, but also LiDAR sensors, radar sensors for other autonomous and driver assistance features, autonomous driver assistance features integration. And so a lot of data is coming into the main SoC, which needs to drive gigabits of data. That's why we have multi-gigabit networks. PCI Express is one of them, which is coming into the automotive due to that. And then we have 1 gig Ethernet, 100 megabit Ethernet, and down to 10 base T1S, which is the 10 megabit automotive real-time Ethernet standard, which is at the end versus CAN FD. In this case, we had 2 megabit, 5 megabit per second data rate, while with 10 base T1S Ethernet, we talk about 10 megabit, an open standard, an IEEE Ethernet standard possibility, yeah, that's basically the difference.
A lot of data to aggregate and move around. So,
Yeah.
okay, a solution for each point. Okay, so 2 questions that seem a little bit related, so I'll try to combine these. Questions are asking about, are any of the protocols proprietary, and another one asking about licensing. So maybe you can just talk about the various protocols and what's required there as far as licensing.
Good question. Of course, there are the LED standards. The LED manufacturers are adding intelligence into the LED. There are some of them which are proprietary standards, of course, like isolate, and they have a licensing fee. But in this case, our customers do not have to worry about that kind of thing, because as soon as you buy a microcontroller which is isolate capable, for instance, for driving to isolate LEDs, the licensing cost is incorporated in our offering.
Okay.
And from the Ethernet side, of course, we are pushing standardized and open standards for Ethernet, IEEE, and in this case, this is a standardized solution and not proprietary.
Okay. And the final question was just, are there pieces of these solutions that can be used in other applications?
Well, when we talk about the lighting endpoint, which is 10 base T1S2 lighting for supporting all these different kind of standards, you can imagine that there are other use cases which also needs very high data rate connection, real-time performance. One of the examples, for instance, are audio applications, and we are also implementing those kind of feature set for an audio endpoint. And the same thing is also sensors and actuator market, a smart sensor. We are also doing these kind of applications and cover this with a so-called control endpoint. So basically, we are trying to roll out a full family, an endpoint-based family for control-based applications, for audio applications, and lighting applications, and there's definitely room for more.
Okay. All right, Stefan, thank you again so much for being with us today and sharing your expertise. Thank you to our viewers for taking some time out of your day. If you enjoyed the episode, please like and share. Please visit us at microchip.com/designs for the edge. There you can see our upcoming episodes out through October 16th. And you can also peruse our previously recorded episodes, both for Designs for the Edge and our other live stream series, Coffee Break. Please check that out and hope to see you next time. Thank you.